Okay. Give it just another minute for people to trickle in here.
Yeah, I think we can start admitting people now if Danica's ready.
Okay. All right, I guess we'll give it, just another 30 seconds for folks to trickle in here. Okay, I think we can get started. So hello, everyone. Thank you for joining us for this first installment of EPSP seminar talk for 2021. My name is Jimmy Geilinger, and I'm going to be the primary moderator today, along with Rissa Madoff, who is our fellow moderator and co-organizer with EPSP Connects. So before we get started, I'd like to mention that next month, EPSP Connects is planning on holding a science communication panel on Wednesday, February 10th. So stay tuned for tweets, emails through the listservs, and more information on this upcoming panel. We're still finalizing speakers for that. But so today, we're excited to introduce Danica Roth, who is currently an assistant professor at the Colorado School of Mines in their Department of Geology and Geological Engineering. And so Danica had completed her PhD at the University of California, Santa Cruz with Noah Finnegan and Emily Brodsky. And prior to joining faculty at Mines, Danica was an NSF postdoctoral fellow in Josh Roaring's lab at the University of Oregon. And much of her talk will be based off some of that recent work today. And so today she'll be discussing her work related to host fire, steepland sediment transport. And as for some general housekeeping, we can take questions through the chat if that's what you would prefer to have in terms of asking questions. And you can also raise your hand and then we can call on you if you prefer to verbally give your question. But we'll save questions for after Danica gives her talk. So Danica, the floor is yours.
Thank you. Can everyone see my screen okay? One nod, awesome. Semester of large undergrad class lecturing has prepared me for this. Okay, so yeah, thank you so much to conveners for organizing these talks, for inviting me here to speak to everyone. Hello, thanks for showing up to everyone who's watching. I would also like to thank my collaborators, Tyler Doan, Josh Roaring, David Furbish, and Aaron Zetlerman, who all contributed to the work that I'll be showing you today, which will be on wildfire, surface roughness, and steepland sediment transport, or to steal Josh's much more exciting summary, throwing rocks down hills. So before I get started though, I just wanted to point out that while I'll be talking about work kind of at the intersection of these three topics, I hope that by the end of the talk, I will have convinced you that each of these is actually a pretty exciting topic of study on its own. And I also hope you'll bear with me as I kind of smash them all together in this talk. All right, so many of you might have noticed that climate change is causing increasingly widespread, frequent, and intense wildfires over the last few decades. For anyone who isn't already thinking about wildfires, this is the current global fire activity as of yesterday, showing the incidence, perimeters, and satellite thermal hotspots. And this was the US fire activity in the middle of fire season last August. So this is actually as bad as it looks. 2020 was a record-breaking fire year in pretty much every sense. This is a nice infographic comparing fires in 2020 with the previous 2 decades. That was published in a New York Times article from September that said, one after another, major wildfires exploded across California, Oregon, and Washington earlier this month. They have added up to the worst fire season on record. This season is part of a long-term trend toward more frequent, more devastating fires in the West that shows no sign of slowing down. And again, this was in September when we still had 3 months left in the year. So what the New York Times and many other major media outlets have pointed out here is something that a large and growing number of studies have demonstrated over the last few decades, that increasing summer temperatures and aridity, sometimes in conjunction with other factors like fire management practices, are causing a large-scale shift in wildfire regimes. Just to highlight a few key points here. Can you guys see my mouse? Okay. So here we're looking at fuel aridity and maximum summer temperatures in California, which have both increased on average since the 1970s. And this is consistent with anthropogenic trends simulated by climate models. Oops. So a number of studies have now shown that these are key drivers of wildfire activity. This is nicely demonstrated in some recent work by Williams and others, who've shown that burn areas scale non-linearly with maximum summer temperatures and fuel aridity on the West Coast. So the outcome of these shifts in temperature and aridity are that fire season length, risk of fire, and the frequency, duration, and magnitude of large wildfires are all increasing throughout the Western US. Okay, so from a geomorphology perspective, how do landscapes respond to wildfire? There are a lot of ways that we might answer this question. So with the disclaimer that this is a really broad and simplistic overview focused on my interests, which are erosional processes, I would answer it by saying that in an unburned landscape, soil is stabilized below ground by root cohesion and above ground by vegetation that both stores sediment upslope and provides protective ground cover. In a wildfire, that vegetation is incinerated, which releases trapped sediment to travel from the hillsides to the channels as dry rubble, and the surface is also now exposed to wind erosion. Then there's also a range of ways that soil can undergo structural and chemical alteration in a fire, which can decrease infiltration and change soil erodibility. Then when rain falls on the surface, we see reworking of the bare ground by rain splash, which creates microtopography, and overland flow leads to the development of rill and gully networks. And then there's a period of elevated erosion and hazards like debris flows and landslides. The hill slopes recover as vegetation regrows and stores more sediment. Channels recover as material deposited into them earlier gets removed by fluvial or debris flow processes. And then finally, over long time scales, assuming some kind of dynamic equilibrium, the landscape should eventually return to a recovered state. So the mechanistic details and timing of some of the processes in this cycle, kind of fire recovery, are still unclear, but looking forward, climate models forecast intensifying winter storms and continuing megadroughts. Some are actually now calling them. So the outcome of that pairing is that more rainfall means more vegetation or fuel, and more megadrought on top of that increased fuel load means bigger fires. When we add those intensifying winter storms back into the mix, we end up with a cycle that ultimately leads to further increases in erosion rates and hazard risk. So conveniently, if you just scroll down the EPSP Connect page a little, you can see a much more in-depth conversation about all of these topics and others from a panel of folks with a lot more expertise than I have on post-fire various erosional and hazard processes. But what I'd like to highlight here is that our mechanistic understanding of many of these post-fire processes is still nascent, and predicting transient responses to fire, whether that's short-term hazard assessments or long-term landscape evolution due to the shift in fire regimes, it'll require flexible process-based models and sufficient data to calibrate them across variable settings. So at this point, I'd just like to pitch some of my students' research, which works toward those goals in a range of ways, from examining post-fire soil hydrology across climate zones to developing techniques to measure post-fire rill network density and surface roughness. So these were all presented at AGU last month, and it's not too late to see them if you missed them then. But for the rest of this talk, I'm going to focus on the questions of how does surface roughness influence post-fire hill slope sediment transport? And how do we fundamentally account for long distance movement of sediment on hills. For example, that released from behind burned vegetation as dry rubble. So these are questions that my collaborators and I addressed in work that we recently published in PNAS, where we looked at particle motion on burned and vegetated hills. And this is where the rock throwing comes in. So vegetation is a form of topographic roughness. And much like in rivers, it can act as a dam to trap sediment and build up wedges, which you can see in this cartoon behind the bushes here and in this picture from the Oregon Coast Range. So as I touched on earlier, wildfire can influence sediment transport in many different ways. A lot of previous research has shown that fire can burn off an absorbent top layer of soil, or ash and chemical alteration of soils creates a sealed or hydrophobic layer that increases water runoff to the point that it's a flow capable of picking up sediment. But fire's effects on roughness are a relatively unstudied topic, and we're still figuring out how much it contributes to post-fire impacts. But we do know that when fire removes these vegetative roughness elements, it decreases the surface roughness and releases trapped sediment to travel down to the valley floor. But this poses a problem because it turns out that commonly used sediment transport laws fundamentally cannot account for long distance sediment fluxes on hills like that. This is actually a much bigger problem than just wildfire related sediment fluxes, although that is where it becomes particularly urgent, I think. But this is the part in the talk where we're transitioning to talking about steepland transport. So the formula that we use to measure sediment fluxes on hills are, sorry, just brain blanked. So we currently use these formulas for maybe linear or nonlinear fluxes. Here, Q is a flux, X is a distance from a ridgeline, D is some kind of diffusion coefficient, S is a slope, maybe SC is a critical slope. So there's a few variations on these. It might be linear, nonlinear. They might include something like soil thickness, but we would call all of these local models in that they are calculating a flux at point X based only on parameter values like slope at point X. So these kinds of models are essentially averaging soil creep processes over long timescales in large areas. And they work pretty well in those scenarios where the soil is approximating a continuum. So particles don't care about upslope topography, and we aren't worried about things like momentum. So processes like freeze thaw, wetting, drying, root bioturbation, or if we're looking at fluxes over long enough timescales and large enough areas that an average rate makes sense. But in steeplands, we often see that transport is characterized by long mean travel distances over the surface. So the soil is not a continuum. And also by spatial and temporal patchiness. So processes are stochastic, things like rock fall, dry ravel, bioturbation by tree throw or burrowing animals. And if you care about actual fluxes, say for high magnitude, low frequency events, a long-term average rate kind of misses the point here. So a lot of sediment transport on Earth occurs in steep regimes. And since we're also closer to the threshold for slope stability, they're particularly vulnerable to catastrophic events and impacts of perturbations, such as following wildfire, where we see large amounts of dry ravel. So dry ravel is the gravity-driven downslope movement. I'm considering it under rarefied conditions, so not a granular flow, although that's another form. So this is a pretty serious flux of sediment. Post-fire erosion rates can be 6 to 30 times higher than long-term rates. And while that elevated erosion might only last a short while until landscapes recover, it can account for 25 to 75% of long-term sediment yields. Oops. It also might be linked to post-fire hazards. Recent work by colleagues has suggested that when this material travels down to valley bottoms, it can then sit there and fuel debris flows the next time that there's heavy rain. So if we want to be able to model and predict this kind of long distance transport, the first step that we need to know is what controls particle travel distances, how far those particles are going. So we can think of a number of potential variables that matter for this kind of sediment transport. But this study involved throwing rocks down hills, which required first carting rocks up hills. So we have to limit our experimental parameter space. So we focused on slope, particle size, topographic roughness, which we expected to be the first order controls on particle motion. And in future, we're planning to consider particle shape, elastomechanics, and others. So to look into this kind of transport, my colleagues and I ended up throwing about 1,000 rocks down a bunch of hills in the Oregon Coast Range. We had 3 different sizes of rocks, a wide range of slopes, and we used both burned and forested hills, dropping 100 rocks on each unique field site combination. So because wildfire removes surface roughness, really in this case, kind of in the bigger picture of trying to understand long distance sediment transport, these burned and vegetated slopes are just providing convenient natural laboratories for examining particle motion over a range of surfaces of varying roughness. Okay, so we can look at the variation in roughness quantitatively by examining the cumulative distributions of micro roughness on these slopes. So we found that the median micro roughness was up to an order of magnitude lower on the burned slopes. And just to clarify, there are a lot of different ways people measure roughness in the literature. So here we are using roughness height as a measure of deviation around the average ground surface. And when I say micro roughness, that's reflecting the fact that we're using a high pass Gaussian filter to filter out roughness that's larger than spatial wavelengths of about 1 meter. And then, okay, so we are also showing the slopes here. So the solid lines are vegetated sites. The dashed lines are the burned or smoother slopes. So you can see that there's about an order of magnitude difference between them. So if we look more closely at the 2 sites in green, these have the same surface gradient, and there's a 1.5 centimeter difference in their median surface roughness. So this is the burned one, the vegetated site. So it's a little bit rougher on the vegetated site, but not by all that much. So we went to these slopes, we dropped all of our rocks, and these are histograms of the particle travel distances on each slope, along with representative hill slope profiles for each of the sites. So first, I just want to point out that these figures are on the same horizontal axes, so up to about 30 meters here, 4 meters here. And the kind of striking thing here is that while around 20% of the particles traveled between 4 and 30 meters on the burned slope, none of them went farther than 4 meters on the vegetated slope. And to reiterate this, so this is the same surface gradient. The median roughness is only 1.5 centimeters higher. So that's a pretty big impact for 1.5 centimeters of roughness. So we take away from this is that in addition to releasing sediment as dry gravel, the removal of roughness by fire also allows particles to travel much farther on smoother slopes because the roughness is not stealing momentum. So we already kind of knew that intuitively, but what we did was use this rock drop data to start developing a framework for modeling these long distance or non-local fluxes. So let's return to these non-local and local sediment transport models, get a little bit more technical. Mathematically speaking, local models are predicting, will predict identical fluxes at any points with identical slopes. So for example, showing an example hill slope profile here. And if we have 2 points, point x1 and x2, with equal slope, as indicated by the little triangles, a local model will always predict that they experience equal fluxes. So the problem with that is that if material is passing through those points from upslope, then they might actually experience different fluxes if their upslope conditions are differing. Right? So we can break this down into the fact that different points upslope, so here some position x prime and a distance upslope of each of our points. And each upslope position could entrain or disentrain different amounts of sediment, where entrain means stuff starting to move, disentrain means it stops moving. So for example, say we're talking about squirrel bioturbation. If squirrels prefer to dig holes in steeper slopes, then you might see higher rates of entrainment from squirrels here on the steeper part up slope of x2. And since the slope is steeper, then any dirt that those squirrels start moving will also travel farther. So more of it makes it past point x2 than would make it past point x1. And a local model fundamentally cannot account for this. So like I said, this is a much bigger question than just post-fire transport. This is all long distance transport that is influenced by upslope conditions. So this points to the need for non-local models to account for those factors. And a few of these exist, but I am focusing on one developed by David Furbish and colleagues, where we are defining the flux at a given position x as the sum of all sediment that's entrained upslope of x and travels at least far enough to pass x. So mathematically, this is formalized as a convolution of entrainment rate at each upslope position, x prime, and an exceedance probability, or the likelihood that a particle that originates at x prime will reach or exceed position x. This is also sometimes called a survival function or the complementary cumulative distribution function. So all this is really saying is that if, say, a squirrel sits at position x prime upslope, then the amount of sediment that I would measure from that squirrel at position x downslope is the amount that he kicks downhill in the first place, so the entrainment, times the fraction that doesn't stop before it reaches me. And then by convolving, we're just adding up sediment from all of the squirrels at every point between me and the ridgeline. I also want to point out this formula is valid regardless of the type of transport, long distance, short distance, or rarefied single particle motion or granular flows. In fact, this is a form of something called a master equation, which was first formulated by Einstein. And it's just a general probabilistic formula that's been used for decades to describe particle motions, literally from atomic to galactic scales. So an example I like to use, I could just as easily use this to describe, say, the flux of clothing that's making it into the laundry as the rate at which I'm like picking up socks and accidentally dropping things as I make my way from my room to the laundry room. This is a completely generalized formula. Excuse me. So in the sediment transport world, though, the way that people have previously tried to distinguish between transport that can be accurately described by simplifying this equation down into the more familiar local flux models and truly non-local transport or long distance transport that can't be simplified is by whether the exceedance or travel distance distribution is light or heavy tailed. Essentially, a light tailed distribution has a defined mean and variance. And if enough particles are traveling far enough that we can no longer define their mean value, that means we have a heavy tail distribution in broad terms. So we can take these empirical travel distance data that I showed you and calculate their cumulative distributions and probability densities to assess an empirical exceedance, or the likelihood of a particle traveling farther than any given position. And then we can see if that distribution is thin or heavy-tailed. But we can also do better than that, because from these I can actually calculate a spatial rate of disentrainment, or the likelihood that a particle that has made it to a given position will just stop there. This is a really important point, because while I'm calculating my disentrainment from these empirical statistics, travel distances, disentrainment is really the physical mechanism that controls travel distances and all of these statistics. So that means that disentrainment gives us a way to finally bridge what's actually a pretty long-standing gap between the empirical statistics of particle motion and the underlying physics that controls them. So that's what we took the next steps toward doing, or the first steps toward doing. Okay, so on the statistics side, we found that a Lomax distribution model, this equation here, does a pretty great job at fitting our empirical travel distance exceedances. We like the Lomax because it can describe both thin and heavy-tailed distributions. We have thin tails for negative values of this parameter A, and then an exponential distribution, which is the dividing line between thin and heavy-tailed distributions, at A equals 0, and then we transition into heavy tails for positive A. So this is getting a little bit abstract. A and B are just mathematical parameters, right? They don't have an intrinsic physical meaning, because this is math, not physics. And so for me, the interesting thing is that it turns out that this model, while just a mathematical model, actually does provide a surprisingly intuitive framework for particle behavior that we can understand in very physical terms. So this is a cartoon showing the theoretical disentrainment, or likelihood of stopping, which again is related to the exceedance rate, as a function of travel distance. And this is what the disentrainment rate looks like for a negative A values, or thin-tailed distributions. A thin-tailed distribution example is shown here in the inset. And you'll notice that thin-tailed distributions in semi-log space are concave down. So we can see that the disentrainment function that produces a thin-tailed distribution is actually increasing with distance, meaning that particles become increasingly likely to stop as they travel farther, which we call bounded motion, since they come up against an asymptote. An exponential distribution, which is linear in semi-log space, is produced by uniform disentrainment rates, so constant with distance, and that's for parameter A values of 0. And then a heavy-tailed distribution, which is concave up with positive A values, is a result of spatially declining disentrainment rates. So particles are now becoming less and less likely to stop as they travel farther, which we call runaway motion. So in addition to defining these 3 regimes of particle motion, which are controlled by parameter A, our initial disentrainment rate, as well as the uniform disentrainment rate, are also both equal to 1 over the parameter B, which means that the distribution parameter B is just the mean travel distance for an exponential distribution, or is the initial disentrainment rate. And then finally, both the bounded and runaway transport or motion regimes are controlled by asymptotes, shown by these dashed lines, which intersect this 1 over B line at a distance x of parameter B over A. So we can think of that as a characteristic travel distance at which particle motion either becomes bounded or runs away. So these are very physical meanings for the distribution parameters. Let's compare this model to our data and we can see how it holds up. Okay, so this is our data. This is a very complicated figure, but we have on the y-axis is the empirical exceedance probability, or probability of particles traveling farther than a given position on the x-axis. And then on the left are all of our vegetated sites. On the right are the burned sites. Each of these figures or subfigures represents 100 rock drop travel distances calculated as distributions. And the slopes are increasing as we move down the plots. And then for each set of 3 figures, we have small, medium, large rocks. So 1.7 centimeters, 4.5 centimeters, and 7.3 centimeters on the intermediate axis diameter. So, and the black lines are the Lomax distribution fit to each data set. Okay, so the Lomax looks like it's doing a pretty decent job overall. It's providing a pretty good fit to the distributions. And as in the cartoon, we can distinguish visually between thin-tailed and heavy-tailed distributions. You can see the concave down or concave up is thin-tailed versus heavy-tailed, associated with bounded motion or runaway motion. So going back to that link to physical parameters, we can also see that, as we might expect intuitively, we are going from thin-tailed or bounded motion for smaller rocks on lower slopes as we move down, and we're transitioning to heavy-tailed or runaway motion on the steeper slopes as we move down and as we move toward bigger rocks. So this is kind of intuitive, right? Bigger rocks on steeper slopes go farther. We can also see that if we plot everything in terms of the disentrainment rate instead of the travel distances, or we can clearly see this transition from bounded motion, increasing disentrainment rates, to decreasing disentrainment rates or runaway motion as we shift to bigger rocks on steeper hills again. And just as a side note, this first vegetated site, you might notice, is a little out of place. I think this actually confirms kind of that we're looking at the influence of surface roughness here, which I'll get to in a second. But because this site, while it's vegetated, it actually is about as smooth as the burned slopes. So roughness is not on here, but we can imagine theoretically, if we're kind of summarizing what we expect to see intuitively, as we increase slope or grain size or we decrease roughness, we expect to see a shift from thin-tailed distributions or bounded motion to exponential or uniform disentrainment. And then finally, on the steepest slopes, the largest rocks, or the smoothest slopes, runaway disentrainment that produces heavy-tailed distributions. And so if we want to be able to actually visualize these things quantitatively, when we look at our Lomax model, if we frame those parameters as slope times grain size normalized by surface roughness, as this combination of parameters increases, we expect to see thin-tailed bounded motion occur at longer and longer distances. And at some point, this transitions to an exponential distributions or uniform disentrainment, and then switches to heavy-tailed or runaway motion that happens at shorter and shorter distances. So I will just repeat that one more time. So this is extending that characteristic distance. So longer distances, exponential, and then heavy-tailed or runaway motion happens at shorter and shorter distances. So in other words, we should see negative A values or thin-tailed distributions approaching A values of 0 or exponential distributions. as our B over A value, or the position at which bounded or runaway motion happens, as B over A approaches infinity. And then as A flips and becomes positive and travel distances become heavy-tailed, then we should see A continue to increase as distributions get heavier and heavier tailed. And at the same time, we should see this B over A parameter decline back towards 0 as runaway motion happens at shorter and shorter travel distances, which means that we'd expect to see something like this, theoretically, if we plotted the bounding or characteristic runaway or bounding distance, B over A, against our physical parameters here, if we think about kind of the physical intuition. And so here is our actual data. And this is another complicated figure. But so these top figures are showing that B over A parameter characteristic distance. And then these two are showing the A parameter and the B parameter for each of our data sets. And then each of these are plotted against slope times grain size over roughness, and then also just against slope times grain size to see variance with and without accounting for roughness. The blue and green boundaries were just hand-drawn to help you see the data clusters. So blue clusters are bounded or negative A values, and green clusters are the runaway disentrainment with positive A values. And recall again that we're expecting to see for B over A an increase for negative A values or the blue clusters and a decrease for positive A values or the green clusters. And showing here to first order, that is pretty much what we see. And if we compare especially to slope and grain size without surface roughness, we can see that normalizing by roughness does shift our data toward the physical pattern that we're expecting. I also wanted to point out that if I go back one slide, sorry. So this position where our B over A value should approach infinity should be at A equals 0 and should really be the place where the kinetic energy gained as a particle goes downslope is balanced with the kinetic losses to surface roughness, so momentum being extracted by surface roughness. So a kind of theoretical value of 1. And 1 is right here. So this is shifting us toward what's a reasonable kind of theoretical range. Interestingly, in contrast over here, when we look at B, the variance in the B parameter is actually minimized without scaling by roughness, which makes sense because if B scales with the initial disentrainment, that means that particles haven't really encountered roughness yet. So we're talking here about the 1 over the disentrainment rate at very short travel distances. So it makes sense that our B parameter is not controlled by roughness, unlike the A parameter. So the roughness dependence is coming from the parameter A. So overall, all these figures are essentially showing us that to first order, the Lomax model appears to be accurately representing the expected physics of this system, while also giving us some insights about the importance of surface roughness in hill slope sediment transport, particularly over long distances. There's a note here to remind myself that D50 probably is not the best characterizer of surface roughness. And we also aren't accounting for things like elastomechanical properties, particle shape, things like that. So this is certainly not a honed model, but for a first order kind of framework, it's doing a surprisingly good job. So I'm leaving myself quite a bit of time for discussion here because I think this is kind of discussion-y stuff. But to conclude kind of what we've taken away from this study, we showed that roughness is a key control on steepland transport. That roughness is measurably decreasing immediately after wildfire, during wildfire. And one of the takeaways is that larger particles are traveling much farther on smoother terrain. So there are implications here for sediment delivery after wildfire or other roughness altering disturbances. So perhaps if dry ravel is contributing fuel to debris flows, if we're transporting the largest particles faster to the valley bottom, this might change the distribution of material in a debris flow. And then more broadly, this Lomax model really provides a unified framework for relating both what we would call local and non-local particle motion to measurable surface characteristics. And I think a big strength here is that in this kind of framework, we don't necessarily need to try to draw a distinguishing line between local and non-local particle motion, which is something that we've previously had to do in order to find analytical solutions. So from the Lomax model, we saw that there are 3 distinct regimes of disentrainment, and those are fundamentally the underlying controls on particle travel distance distributions. And we can link those to physical parameters. So just as a first order approximation, again, as the SD over D increases, those particle travel distances shift from thin to heavy tailed, and that B over A parameter tracks the transition from bounded to runaway particle motion. And I should also say that my collaborator, David Furbish, has just published several papers that go into the underlying physics and theory of this model in much more detail. So this is a first order and empirical check. So I think, personally, I think some of the more exciting discussion points here is where this can go, because what we've done here is a first order framework, right? But the true strength of all of this is in the non-local transport models. Right now, we just cannot account for short time spans and spatial variation in these kinds of fluxes. But with better characterization of those control variables, so things like roughness, the particle shape, full grain size distribution, initial kinetic energy, elastomechanics, all of that, and maybe with spatiotemporally variable Lomax parameters. So if those A and B parameters can vary along surfaces, if we can, rather than back calculating a Lomax, we can forward predict it. With work on those fronts, eventually, if we can connect this model to the full non-local convolutional model, that gives us the ability to start really assessing fluxes and morphodynamics across scales. So for example, using non-local models, we could start getting at details of particle interactions and feedbacks between grain size distributions and surface roughness or surface evolution. And we can also start connecting theoretical fluxes to actual erosion rates, say for burned and vegetated field sites like these, using, say, short-lived radionuclides. So this opens up a wide range of pretty exciting problems that we do not fundamentally have the ability to predict in real sites right now. And I think the fact that we can use, say, high-resolution measured topography it kind of makes this a particularly exciting area of development. So that is all I had. And I guess I can take questions at this point.
Yeah, that sounds good. Thank you so much, Danica. Let's give it up for her for a fantastic talk on these really important issues. And so feel free to type your question into chat if you prefer, and Risa and I will read those off, or if you would prefer to do it verbally, you can also raise your hand as well, and we'll ask to unmute you. So yeah, Katie Barnhart, I guess I'll ask you to unmute.
Hey Danica, that was a great talk. I'll sort of read my question and expand on it, which is, I'm curious whether the roughness you report from the vegetated hill slopes reflects the bare ground alone or the bare ground and the vegetation. And depending on the answer to that question, sort of what the relative contribution for stealing momentum and also providing stopping spots, the sort of vegetation itself provides, as compared with the surface, the unburned, rougher surface itself.
Yeah, that is a great question. Thanks, Katie. Let me find, hopefully I've included an extra slide with those distributions in here. Computer's thinking. Okay, so these are the full, these are all 7 of our sites with the histograms, and both the high pass micro roughness surfaces are the thinner lines, and then the low pass surface or the longer wavelength surface that we filtered out for this study those are shown in the thicker lines. And then for reference, because these are different horizontal lengths on the x-axis, I'm showing my mouse is all laggy. Sorry, I'm showing all the same horizontal distance. I think it's like 2.5 or around there meters, just for visual comparison of the roughness. So, and then again, these are ordered the same way that those exceedance and disentrainment plots are. So this is vegetated sites and burned sites, and steeper slope as we go toward the bottom of the slide. So with all that set up, yeah, we can definitely see the places where particles stopped, in particular on the vegetated sites. For example, this is our steepest, most vegetated site that I showed in the video with the giant trees. And you can see, sorry, I've got the little zoom window thing is blocking my screen here. So you can see, for example, where we have collections of disentrainment that are associated with things like roots or fallen logs or stumps or trees. So these big spikes, and it does look like if the smaller scale roughness is large enough, then disentrainment is dominated by the sharp bumps, basically. Here, for example, the macro topography is going down slope here. So if it's not for roughness, we should be seeing less disentrainment here, right? But this is, I believe it was a stump that clearly collected a lot of particles. On the smoother burned surfaces, in the absence of surface roughness from vegetation, we do see some disentrainment around the broader macro topography, but it's a lot less, it's a lot more variable, I guess I'd say. So, and I guess I should also say that these are representative transects. We did do quite a bit of comparison to try to make sure that we weren't picking like a particularly funky transect or missing a bump that looked like it was disentraining a bunch of things. But this is a single transect through a several meter wide swath. So each individual transect here isn't necessarily representative of the entire drop zone surface. Let me see, did that actually answer your question?
Yeah, that was great. Thank you for that detailed sort of discussion in the context of this figure.
Okay, we have Sebastiano. He's asking, he said, very interesting presentation. He's interested in reading more. He's interested in connecting, hold on a second. He's interested in the connection of geomorphic studies and surface roughness and sediment connectivity, and how those relate to your experimental studies, if they do. So how does sediment connectivity relate, if it does, to your studies?
Hey, sorry, hi. I'm in another, unfortunately, I can participate only for some portion because I'm in another meeting, very boring meeting about my department, but I'll try to ask. Yes, I'm thinking that geomorphometric studies conducted on high resolution digital terrain models that focus on roughness and also on sediment connectivity can be strictly linked with your experimental studies, and maybe some synergy between the two approaches can be quite interesting. So I will read more about this research if there is some paper around.
Yeah, so I think if I'm understanding correctly, are you pointing at some of the geomorphometric studies that are trying to characterize surface roughness? I've seen some studies on this for things like micro peat or micro roughness of peats. It's really interesting in the literature how much the measurement of roughness varies. It seems like there are a lot of different ways that we can measure roughness, and they have not really been compared quantitatively or systematically to see kind of what do they each characterize best. But I do think there's a wide range of literature out there that's that has a lot to contribute on the measurement of roughness. And I think especially, and this is maybe kind of also jumping ahead to David Millage's comment about colluvial grain size distributions, I think there's some really interesting questions around the connectivity between surface roughness, grain size distributions, and mobile distributions. So you can imagine if you start with a certain distribution of sediment, you entrain things at a different rate based on grain size. They travel different distances based on grain size. And then once any of them stop, they create new surface roughness that then nucleates a new collection of grains around it, right? And then that further alters the distributions. These are complex feedbacks, and I think both better and more systematic measurement of surface roughness, more experimental data on grain sizes, and in particular, I think this is one of the potential areas where a true non-local flux model could be deeply meaningful and give us an actual quantitative mechanism for modeling these kinds of feedbacks at a kind of particle and surface topography scale. I don't know if that directly addressed your question.
Okay. Is it?
Yeah. I guess it sounds like it did. So,
okay,
and it sounded like you had already kind of jumped ahead, but maybe we could elicit more discussion on it from David Millage. So, do your findings mean that we would expect colluvial grain size distributions to vary down slope in some landscapes?
Yeah, I don't have a good answer to that question, but I think it's again like kind of one of these exciting fallouts of this work is maybe Tyler Dono and I have tried some kind of thought experiments around, we end up with kind of steady state in equilibrium, or does this mean we would end up with some kind of runaway change in grain size? Like what's, we haven't managed to close that loop yet, but.
Danica, Danica, could I ask a follow on, or just, the first answer is great. Like, let's try it. But I guess my question would be, if there was going to be anywhere where you could go, because you're going to go and dig holes in hills, so you kind of want it to work. So if there was going to be anywhere you'd go to find downslope sorting, coarsest grains at the bottom, probably, where would you go?
Well, so I would say there, and I should have mentioned this initially, there are observed downslope coarsening systems on Earth. This happens very commonly on colluvial slopes, or oh boy, I'm blanking on the word for it, like scree pile. Oh, someone help.
Talus,
Talus, that's it. Thank you. Oh my gosh, this has been happening so much lately. Yeah, so we see downslope coarsening on talus slopes. There's also been some observed on deltas and other places where preferential kind of grain size dependent travel distances or sorting have been presumed to be the explanation. So I would say maybe go to a talus slope, but I would also say maybe collect data and then try modeling to see if you can explain it with a reasonable actual distribution that matches with measured distances the particles travel.
Okay. I think Kristen Sweeney, did you want to ask your question, or should I read it?
I can ask it.
Okay.
Yeah, so I enjoyed your talk, Danica. So I guess I was wondering about like the spatial structure of roughness in these places, and like whether you've thought about how that might or might not matter for your travel distances. So I'm just thinking about like sword ferns, like if you have them kind of like randomly arranged, or if they're all in a line, you know, like parallel to the slope, or if they're all perpendicular to the slope. And yeah, so just sort of like if there's a directionality to the roughness, if you've measured it, and if so, what impact do you think that would have on your measurement?
Can you clarify, what did you mean by if they're all parallel to the slope?
So I mean, I guess, yeah, maybe sword ferns aren't a great example, but like maybe thinking about instead like trees that are planted versus like a quote unquote natural forest. So, you know, like in these places in the Coast Range, for example, that have been logged a lot of times the trees are planted in rows versus being like kind of more randomly distributed, and whether those rows create like preferential pathways either for disentrainment or entrainment of particles.
That is a really interesting question. I have not thought about the spatial patterns of tree plantings, but I think that's an interesting kind of thought experiment. And I'm hunting for a supplemental figure that I seem to have not actually included in my extra slides here. Oh no, here. Okay, so this is just a long slope variation. And I should say that we did not look at horizontal variation in roughness here. But I do think that we did see the influence of preferential pathways. There were some, you know, clear places where particles piled up and we had to remove them before they created roughness feedbacks. So I think that's important. And maybe I should have mentioned that in response to Katie's question. But so while we didn't systematically look at the cross slope patterns in roughness. One thing that we did see was, so in this figure I'm showing, this is that the high pass roughness or the micro roughness that I used in this talk. And then on the right is again, that thicker line shown on the transects, the low pass or filtered long wavelength roughness as a function of slope. And then the solid symbols are the vegetated sites and the open symbols are burned. So the interesting thing here is that we're seeing the high frequency roughness kind of, it's got some kind of slope dependence, which is my original takeaway from this figure is that we're seeing like some kind of high frequency roughness that like burns away here, which we can tell from the slope dependence. But to get at your question, and I think this is a slope dependence for the surface roughness. And I think that that is reflecting basically the fact that as you go to steeper and steeper slopes, the soil is thicker, because in order to, the Oregon Coast Range, as you know, it's pretty steep. So to find low gradient sites in the same area with the same vegetation characteristics, as close as we could, we were mostly kind of going along the same slope. So the low slope sites are closer to the ridge line, and the high slope sites are farther down where the slopes become steep and planar. So I think the soils are thinner, closer to the ridge line at the low slopes or at the low gradient sites. So, and I think that that's reasonable. There's some work showing, particularly in the Coast Range, at least that I'm aware of, showing that some forms of roughness can be slope dependent, maybe linked to this kind of pattern. But I think also linked to, especially with biotic factors, there can be slope preferences. So I think that definitely I would expect to see variation in the influences of roughness as you travel downslope. And I think at the level of preferential pathways of particles, like I said, that's a cool question I have not really considered, and I'm not quite sure how to answer, but it's very interesting. But I do think at the kind of larger scale, horizontal difference between like an area that had a recent landslide is more smoothed, or if I'm sure you've seen, for example, Brooke Hunter's work looking at the effects of land use on post-fire, various post-fire factors. And you can see in Oregon these clean lines between areas that are owned by logging companies or not. So for example, in those places where there's variation in roughness, I would expect to see big differences, and they might be really interesting if it's kind of a clean cut across property lines. But that might not be exactly what you're getting at. That's pretty long-winded, sorry.
No, that's great, thanks.
Cool, yeah, so we got lots of great questions still rolling in. This is one question too that, yeah, it definitely is of interest to me and a lot of, I'm sure, the post-fire community is, so overland flow, this is from Paul Richardson. Overland flow is clearly important at many burned hill slope sites. Any thoughts on combining the model you presented with a runoff model to predict post-fire sediment transport?
I'm so glad that you said that, Paul, because I am working on a proposal right now to hopefully do that. Yeah, I think so. I'm still, I think I kind of was mentioning earlier, I'm relatively new to the post-fire research community, and there are a lot of people out there who know much more than me about overland flow and all of these post-fire soil alterations. So I'm still kind of developing my worldview on this, but I think that if we kind of consider surface roughness and soil infiltration on like soil erodibility as these kind of primary axes on what's controlling post-fire erosion, I think it's it's an interesting question to try to combine these into like the parameter space that really controls various kinds of erosion. And I think I'm probably rambling here because I have not fully developed my thoughts around this, but hopefully I'll manage to do that in the next couple of weeks. But I think it's a great question, and yes, I am thinking about it, and I would love to talk to you more if you also have thoughts on that.
Okay, thanks. Tyler was recommending an article by Sarah Williams that's in the chat. He provides a link, and it considers particle shape and size. So you all can look at that. Also, Nakul had a question. Let's see. Can you speak a little about how you think the transit, let's see, to tumbling from an immobile state? Let's see, as they, trying to outline this. Nakul, are you there?
Yeah, I'm here.
Can you clarify your question a bit?
Sure.
Okay.
Yeah. Hi, Danica. Thanks for your talk. My question is, you know, these particles are sitting on hill slopes not moving, and then something makes them move. And in your experiments, you dropped them physically. So I'm just wondering what you think about the mechanisms that makes this stuff move, how that transition happens, and if it matters at all for all of the stuff that you outlined in your talk.
Yeah, thanks, Nicole. That's a great question. So maybe first I should highlight that our experiments were not intended to really imitate the physical initiation of motion for particles. We were starting with I think, I'm forgetting if it was 10 or 20 centimeters of drop height across all sites. And that was specifically designed to kind of get our distributions into a range of travel distances that would let us learn the most about the distributions, not represent the actual erosion rates or transport rates at these sites. But what we're really talking about is the initial kinetic energy, right? And the initial entrainment rates. So my colleague Tyler is much more versed in the entrainment than I am, but and I don't know if Tyler, you want to weigh in here, but my thoughts on this, I guess, are that if we're talking about sediment that's just sitting there, there are a number of ways we might initiate motion. In a post-fire setting, firefighters will tell you that a lot of the dry gravel you can hear coming down the hills during the fires. So I think the initiator there is literally the vegetation has burned and there's nothing holding these things up, and they're just free tumbling. So removal of a barrier. So maybe if you're trying to get at a more representative kind of travel distances for real sediment in a real setting, like if you pile it up and remove a wall, that might be a better experimental representation. I also think once you have sediment that's sitting somewhere, it's got some amount of potential energy, and in some cases probably just takes a little disturbance. So, I mean, I'm sure many of us have knocked gravels downhill as we're just walking. I think biotic disturbances are a driver, probably wind and just very, I think also, you know, anything that's shaking the ground. There's another area of my research, but kind of seismic perturbation of sediment motion is a potential driver. But those things are a little harder to represent through an experiment.
Cool.
Oh,
go ahead.
Oh, sorry. So just to quickly address the other, the transition to tumbling, I also wanted to mention we saw a pretty distinct transition for our particles between sliding and the tumbling that Nicole mentions. And that is something that David Furbish addresses much more in his work. But I think the transition from sliding motion like Coulomb friction dominated motion to something with angular momentum. Angular momentum is a lot harder to steal. So I think that's an important part of this problem. And that seems to happen kind of when particles either get up on a long axis or run up against a bump that, that redirects their motion.
Got it. Yeah, and it sounds like, yeah, the next question is semi-related too. So from Andy Wickert. So thanks for a great talk and for showing convincingly how useful the Lomax distribution can be. Do you have any thoughts on whether a similar formulation could be used for fluvial sediment transport and perhaps help to describe a continuous transition from initiation of motion through various bed load motion types and into suspension? And he had in parentheses, I'm trying to think of turbulence versus fall velocities, i.e. the Rouse number, would create a similar scale to the way you're thinking of roughness on hill slopes.
I have thoughts. They're probably not clear enough to bother sharing here, but we should definitely talk about this. I am really interested in trying to apply non-local models to a range of different systems. And I think that there are already a lot of parallels we know about between fluvial systems and hill slope systems. The thin-tailed versus heavy-tailed distribution, which I just realized David Furbish would probably be embarrassed because I really should be calling these light-tailed distributions, not thin-tailed distributions. I apologize. But so that transition from light-tailed to heavy-tailed transitions has also been observed in rivers by a number of studies, and in particular around the association of roughness into the stream channel. So I think the Lomax model is a thin to exponential or light to exponential to heavy-tailed distribution model. I think anything that follows those distributions can be represented by it. The physical scaling of parameters obviously will probably be different, but it's just a distribution form, right? So I think in the same way that non-local convolution can be applied to any sediment transport, I think anything that has a distribution should be modelable through it. And it's a very convenient distribution form. But obviously the physics are pretty different in a river. So I guess long story short, Andy, we should talk.
Okay, Danica, thank you very much for an excellent talk, and we had a great discussion. That was great. I'd like all of you to join me and join us in thanking Danica, and we'd like to thank all of you for attending today, and we look forward to your attending future panels and talks. Please stay tuned through emails and Twitter, or you can check the EPSP website and be sure and register for upcoming talks. All right, thank you very much.
Thank you all.
Good day. Bye-bye.
Okay.